Hi, this is Grimmer Nest, and this is my project for assignment 2, CSC 480. So in my project you can choose min-max, min-max Prone. So I'm going to do the min-max Prone with a depth of 8. What my strategy is to get most columns as possible, and then go upwards. It seems to just progress on its own, and but since I have more columns in the end, I get a better score. And as you can see, I won with that stretch. Okay, so if we look at how my game was modeled, we can start with my board. And the board is actually a two-dimensional array of characters, X's and O's. And this is a good way to look at it. It's basically just of size 9, and then all their blanks are done, and then the board is returned. If we take a look at how the moves are done on the board, we can look at our max node. So for each node, it's going to set a value. This comes from either the computer or from the player. So if our board has a character already on the specific one, the player is putting as an input, it will go one higher and check if that one's empty. If it's not, it will still go one higher. And whenever if it finds one, it will put that character there. As for our scoring function, if we look at our border service, the score function is divided by 2. The score takes up for 2 points for up, left, right, and down, and this is the function. And actually, since it's done this way, it's always going to duplicate, so we need to divide it by 2 in the end, and then we return the score. The other score function is for diagonally. Works the same way. We check diagonally, but we get a score for 1 instead of 2. Same thing, we're going to do this twice, so we're going to divide it by 2. If we move on to our successor functions, we can look at one of the nodes. And one of the nodes, for all nodes, they have children nodes. And these are expanded by our successor function. Successor function wants to know who it is, if it's the player or if it's the computer. And if it's a max node, it's a computer. If it's a min node, it's a player. That's why there's an X in here for the max node. So if we look at the successor function in the board services, we can see that we make a temporary array list, and then we figure out if this move is valid. So we make a temporary array list, and then we need to know our depth, because we can always hit a board state which we already made, so we don't want to do that. So we always check our depth. If our depth is our depth is not empty and our row is greater than 0, we go up the state. So if we find empty spots, we know this is the next state. And I have duplicates too, so we make sure there's no duplicates, and then we can add it to our list as a child. Okay, so to look at our how we get our values, we have to look at our min-max algorithm. And the way it works is that we always assume our worst case scenario in the beginning of the tree, because we don't have any values. So our best score for a minimum would be max, our best score for a maximum would be minimum. As we progress down the tree, we will hit some leaves, and our leaves will tell us our score. If we like 6 down deep, we have a lot on our board, and we can like figure out a score. This is where it stops, and it also checks if the board is full, it's going to stop as well. It will give us a score, and then we'll go back to our current score, our previous score, and that way it will set the node. When we're finally done with all that, we get to our source node, and we can return the best score for a game. And the game will always get the max score from this algorithm, and then it will go through its children, and if that max score is the same as one child, it will take that, and that will be the next state. Okay, so for our minimum max prune algorithm, there's actually two variables which we add, which are called beta nodes and alpha nodes. And these I definitely always compare them to like ranges. So my beta will be the upper bound, and the worst case for a beta will be the max value. As for our alpha node, that will be our lower bound, and the worst case will be the minimum. So if we look at the min-maximum Puma algorithm, we can see it's very much like the minimum max, except we have our ranges down here, which we keep an eye on. So if we get a score that is outside our range for alpha, there's no reason to traverse that tree, so we can break that off. Same thing goes with the beta. If there's a score that's outside the range of beta, we can break that up as well. And the rest pretty much works the same way. This is a more efficient way of getting it.